So chapter 8, pollution, analysis and policy. So there's three key questions we'd like to ask in this chapter. First, how much pollution is acceptable? Now, we're going to try to develop a definition of an optimal level of pollution. Right? More specifically, what's the optimal level of pollution reduction? And second, we're going to talk about what are the tools that we have to control or reduce pollutions. And finally, we'll talk about under which circumstance are those tools the most cost effective, and what are the pros and cons for each of those tools. All right. Now, so let's begin with this picture. This is the picture we have for ecological economics, that economic system, economic cycle is a subset of the greater ecological cycle, and we need economic production to sustain our way of life. However, right, our economic production creates outputs in form of pollution and waste. Now, some of those pollution it gets absorbed in the sink function and gets put back into the natural input and gets reintroduced as the factors of production, but the rest of it becomes pollution. All right, so one question that we would like to answer is what is the optimal level of pollution? Now, the first definition we've introduced back in chapter 3 is that the optimal level of pollution is the level that results from the amount of production that maximizes total social welfare. Now, the focus here is on production of goods. Right, so for example, if we decided that society optimally we should produce 1,000 automobiles, then whatever pollution that comes from that the production of the 1,000 automobiles, we would deem that to be optimal. Right? So the pollution is an afterthought. The focus is on production. Right? Here's another example. Right? We've seen this model before, where we can categorize QM as overproduction because there's an externality. Right? So we have a relative optimal here. We can say that this is the optimal, this is overproduction. And why is this the optimal? Well, that's the optimal because Q star is production where the social marginal cost equals the social marginal benefit. Now, this condition, right, is called the equal marginal principle. Right? So where the SMC equals the SMB. And the equal marginal principle states that if this is true, then the total social welfare is maximized. Okay, and again, up to this point, we have use this condition to decide what is the optimal level of production, and then whatever pollution that comes from it, right, then we will accept that as the optimal level of pollution. Right, however, that's not very realistic, right? In most real world applications, we have an industry that's already polluting, and when we go in and we try to take care of the problem, the question we're trying to answer is, well, how much pollution should the industry reduce? Right? We don't care about how many iPhones that's optimal, or we don't care how many automobiles is optimal. Right? What we care about is what's the most what is the amount of pollution that should be allowed. Now, of course, ideally, the optimal or at least the ideal level of pollution is zero, right? But we still need economic activity, right? So we want to try to develop a definition for optimal. Okay. All right. So if we're gonna what we're gonna do is apply a variation of the equal marginal principle. Okay, and that is the balancing of the marginal cost and the marginal benefit of pollution reduction to obtain an efficient outcome. Okay, so we're going to develop a new model that's going to look like this. Let's build this model up piece by piece. Okay, so first we'll start with the line on the right here. That is the marginal damage from pollution. So imagine that here, starting from the left is 0 and all the way to the right, this is the pollution level. And Qmax represents the amount of pollution by the industry if unregulated. Okay, so this is with no regulation, this is how much the industry will pollute, right? This is, think of it as their profit maximization. There's no reason for the industry to pollute any more than this. Now, the marginal damage from the pollution follow this upward sloping curve, right? When you read something like this, the underlying assumption is that in the beginning, when the pollution level is low, each ton of pollution, right, does a relatively small amount of damage. However, as the overall pollution level increase, right, when the absolute pollution level is high, then the marginal damage, right, is also high. Okay? And so a marginal damage will have an upwards trend like this. And so the benefit, right, in our model is the pollution reduced, the pollution, this marginal damage avoided. Okay, so when we read this graph, we want to start from the right to the left. Right, we start with the Q max, and we're going to ask ourselves the question, right? Or we're going to say that, well, as for every unit of pollution reduced, then we can avoid. This is the marginal damage. This is the marginal damage that we can avoid. And you see the property here is that as we reduce more and more pollution, the marginal damage that we can avoid decreases, meaning there's a diminishing marginal benefit from pollution reduction. Okay. Now, on the other side of the curve, we have the marginal cost of pollution reduction. Okay, and so this is a downward. So this is from left to right, downward sloping. Okay. So, or here, let's read it from right to left. I think it's easier, more intuitive. What this means is, again, starting from Q max, the first few units of pollution reduction is relatively cheap, right? And then as you ask the industry to reduce more and more pollution, each additional unit of pollution reduced, the marginal cost is increasing. Okay? And typically we will assume this exponential increase as like so. Right? So you can imagine that for an industry where the pollution level is almost zero, they simply cannot reduce pollution anymore. Right, because to reduce that last bit of pollution will put the industry out of business. So we can assume, or we will assume, this marginal cost going up to infinity at that point. All right, so we have. So this graph going from starting from the right, because this is the status quo, and we're asking pollution. We're going to start reducing pollution here. So putting the two graphs together, then we can see, we can see that Q star is where the optimal level of pollution will be. So we will start from Q max and reduce all the way to Q star. So Q star. So just be careful here. Q star is not the amount of pollution reduced. Q star is the pollution level. The amount of pollution reduced is the difference between Q max and Q star. Now, why? So, all right. So, why a Q star? Well, so starting at Q max, right? How much does it cost to reduce emission here? Well, it's very low. So marginal cost is very low, but the benefit you get, right, is really high. So so it is efficient from a societal point of view to reduce emission. Now, so as long as the marginal damage is above the marginal cost, right, it is efficient to reduce the emission. However, once you pass Q star, then it is no longer efficient because the marginal cost of reduction is higher than the marginal damage. Right? So you would be spending more money, right, to avoid a lesser, in monetary values, a lesser amount of damage. Right? So Q star then will be the optimal level of pollution. Okay? Or and Q max and the optimal level of reduction will be from Q max to Q star. All right. Now, let's look at some of the let's interpret the area. Suppose we regulate the industry to pollute only at Q star. So what is A? Okay, so look under the marginal cost. Right, A is the area under the marginal cost curve. So therefore, A is the total cost of pollution reduction from Q max to Q star. That's the monetary values, the total cost, okay, of the reduction. Now, what's A plus B then? Okay, so look under, so look at which curve this is under. This is under the marginal damage curve. Okay, and so this is going to be the total damage avoided from the pollution reduction. So we get this pollution here is no longer happening, and so this total area on the bottom is the total damage avoided. Okay, then what is B? Well, you take the difference between the two, and B then is the net benefit from the pollution reduction from Q max to Q star. Okay, and at Q star, B is maximized. The net benefit from pollution reduction is maximized. Right? We don't have to prove it here, but it is a mathematical fact that if you reduce beyond Q star, then the net benefit of pollution reduction will be smaller than B here, right? And obviously, you can see pretty clearly that if you don't reduce to Q star, if you stop anywhere here, then B will be smaller. Okay. All right. So now we can begin talking about the different types of pollution control policies.